There's a difference between being wrong and being stupid.
What happens when the boldest minds in science admit they could be wrong? How should scientists balance arrogance and ego? And how can having a dose of humility drive breakthrough discoveries? Embracing mistakes and challenging assumptions, daring to be wrong, can lead to groundbreaking discoveries in cosmology.
You're trying to discover something or see something that no one's seen before.
Here today to explore these thought-provoking questions and more is Rocky Kolb, an inspiration to millions and a renowned astrophysicist and professor at the University of Chicago. With decades of experience exploring the mysteries of the universe from dark matter to the Hubble tension, Rocky shares his insights and thoughts on the interplay between ego and humility in science.
In some sense, we are all blind watchers of the sky.
Join us as we dive deep in this in-person interview recorded this summer at the University of Chicago to explore the mysteries of the cosmos with one of my biggest heroes, Rocky Kolb. Let's go.
Rocky, thanks for meeting with me.
Well, I'm happy to do it.
So much fun. Always been a big fan of your career, and we've had too few opportunities to meet in person, but you're gracious enough to lend me some of your summer vacation. I really appreciate it. You're a fan favorite on the podcast, so it's just a delight. So I should say that we are at the University of Chicago, where you have been for how long?
Oh, well, in various roles since 2006, 2007,
okay.
Something like that.
Okay, so it wasn't quite as long as I thought. You are, of course, known for being the co-author with a past favorite on the podcast, Michael Turner, who was on last year and had the kindest things to say about you. And that book...
I won't return it.
Well, what we do, and I should have brought my copy, which is 20 years old, of Blind Watchers of the Sky. And we do a little shtick on this podcast called Judging Books by Their Covers, which you're not supposed to do, but how the hell do you know about a book other than the cover? That was a wonderful book. I read recently just the intro of it, but I've read some of the reviews. And some of the reviews are from former students that not only bought the book, which is the most important thing.
That's the important thing, right.
But took a class with you and where that was kind of featured. So what are blind watchers? What does that mean? What was the origin, the genesis? Walk us through the cover, and we'll show an image of it in post-production. But talk us through the title, subtitle, cover of that wonderful book.
Blind Watchers of the Sky comes from a quote from Tycho Brahe, a great astronomer of the 17th century, 16th, 17th century. And he did not have a high opinion of many of his colleagues. So he observed a supernova in 1572, and he determined that the supernova was far away. It was what he said beyond the moon. He could not determine a parallax of the supernova. And this went against Aristotelian ideas that anything that changes in the universe is due to human corruption. So it had to be closer to us than the moon. And many of his fellow astronomers disagreed with him. And he wrote that, O crassa ingenia, O caecos corli spectatores, O thick wits, O blind watchers of the sky. So this is a theme that runs through this book, that in some sense we are all blind watchers of the sky. And I go through the lives of many of the great astronomers and physicists and heroes, Newton, Galileo, and they were all wrong in some ways or another. And astronomy and physics and science is hard. And the easiest person to fool is yourself.
Right? That's fine said.
And it's something that we have to always look out for. And I think we have to be humble and realize that some of the things that we think, certainly it's true, nobody argues with this, will turn out to be wrong.
Yes.
And humble scientists are not easy to find, but we should all have a little humility.
That's right. I think I always say that you need to kind of balance these two traits of chutzpah, arrogance, ego, with the extreme humility that you're very much likely to be wrong. And pivoting to that, I think it was in that book that you mentioned this quote, and it dovetails nicely with what you just said, from Galileo, who said, our job is to measure what's measurable and make measurable what is not yet so. And we're trying to do that. We build instruments and stuff. But these these characters were tremendous egos. I mean, I think back whenever I get a nasty comment on the YouTube video, I won't get them in for this conversation. It's too wonderful, I'm sure. But I'll have on somebody and they'll be like, "Oh, it's so arrogant," and blah blah blah. And they criticize Bruno too, and he turned out to. My rule is anytime you compare yourself to Bruno, Galileo, or Einstein, you've got big problems. And I say, well, you're very much like Bruno in that your brain is dead and it's completely fried. Talk about the personalities, because Galileo, who's one of my favorite, if not my favorite scientist, in fact, you're standing in the presence of greatness, Rocky. I was tasked with doing a book review of Galileo's dialogue. And my favorite medium is audio. And so I said, I'll just download the audiobook. It doesn't exist. I found out that the University of California owned the Stillman Drake translation, definitive translation of dialogue. And I made the first ever audiobook of Galileo with Carlo Rodelli, Frank Wilczek, and Jim Gates. And
who is Simplicio?
So Simplicio was my friend Lucio Piccirillo. So Carlo was Salviati. I was Sagredo, the kind of interlocutor. And then we had Fabiola Giannati read Galileo's dedication to the Grand Duke of Tuscany. But these were arrogant individuals, and I love Galileo, But talk about the personalities and really, what does it take to? You can't just be humble, but you also have to, have a little bit of chutzpah. So how do you balance that?
You also have to be fearless, because you're trying to discover something or see something that no one's seen before. And, you have to believe that you can do something that other people have not done. And you're right. It's a real balance between chutzpah but you should still keep in your mind that you might be wrong.
And of those characters and the people, I would say you should aspire to make blunders like Einstein. Was there a particular, story of an astronomer or, maybe even someone lesser heralded, like, Henrietta Leavitt? I talked with Wendy earlier about her career. Talk about some of the personalities. What are these like as individuals? I mean, a guy like Vesta, with a name like Vestos Life. This guy must have been fun at parties, right?
Yeah. So, a local hero around here, of course, is Edwin Hubble.
Yes.
And, there are others also. But I keep in mind this phrase that you should never meet your heroes.
Well,
because
I gotta go. No, just kidding.
Because they are all human.
Yes.
And they all have, personality flaws. And when I was an undergraduate, a hero of mine was Schrodinger. Developed quantum mechanics, and he had philosopher.
DNA,
and all sorts of things. But his personal life was rather distasteful. We'll just leave it like that.
Get Me Too'd.
Yeah, nowadays, right? I mean, he would not survive in this era, and possibly he shouldn't have survived in the 1920s and 30s.
That's right.
So you should never meet your heroes. But that said, there are redeeming values in all of them, and you can admire what they did, and you can also realize their mistakes. And I think it informs my research. And I always think that if I would ever be wrong, it hasn't happened yet, but if I would ever be wrong, I would admit it.
What was it like working with Willie Fowler? He's a local hero in Southern California, at least.
Sure.
What was he like?
Well, Willie Fowler was a real hero of mine for a couple of reasons. One is I saw what he did in his career at Caltech. He started the field of nuclear astrophysics, and his training and his education was in nuclear physics, and he applied it to astrophysics. And I think that the people who came out of Willie's group, there's a long list of names who are very famous, and I would list them, but I'd leave one out, and you would get a bad email or something.
We'll just mention George Fuller, because he's my colleague. Yeah.
George Fuller was my office mate at Caltech. So I saw what Willie did, and I also saw that he had a quality that I think is sadly lacking in our community, that he appreciated and celebrated the accomplishments of people around him, even if he wasn't involved. So his students and postdocs, he just loved when we did something that he thought was good. And he, talked to people about it and supported us. And even if he wasn't involved in it. And that's, I had many postdocs and students and people at Fermilab and at the University of Chicago, and that's always inspired me to appreciate what they've done, even if I wasn't involved.
Yeah, in a way, your mentorship of your students carries on his legacy as well.
Right. And I think George Fuller feels the same way, and Dick Bond feels the same way.
He's a good friend, a member of the SO community as
right.
well.
And Willie also told me, don't be afraid to be wrong. There's a difference between being wrong and being stupid. So don't be stupid, but it's okay to be wrong. It's okay to risk a little bit.
Yeah, you need that kind of permission sometimes to dare greatly. And I think about him, I think about kind of a polymath that may not exist anymore. I mean, there was one a couple of feet over here, Enrico Fermi, right?
Yes.
Who could do theory, phenomenology, and he could do experiment. Willie was sort of in that same mold. I want to ask you, as you're not an experimentalist, you're very conversant in it. What is sort of the experimental minimum? If you're teaching and mentoring a student, what's the minimum she or he should know about my craft of experimentation in cosmology, astrophysics, particle physics in general?
Errors. What does an error mean? Systematic uncertainties, statistical uncertainties, and just to get an idea of what goes into experiments and how things can. Experiments are hard. So another mentor of mine was Leon Letterman, who was director of director of Fermilab, hired me at Fermilab, and he would always say that experiments are hard, and once in a while you can get something to work, and it's beautiful when it does work. So appreciate how difficult experiments are, and that the experiments may be underestimating the errors, or maybe overlooking something, but pay attention to it. But I don't think, as scientists, we should believe things. I think belief is a word that's very dangerous.
Faith. Yes, exactly. I say I don't believe in gravity, and people are like, you're an astronomer or a physicist. So I was talking with Wendy earlier about that, and she always makes this distinction between accuracy and precision. And I know you've talked about that too. Like, we have enough, precision cosmology for a lifetime, but we need accurate cosmology. And I think the thing that I didn't appreciate until I was a much older grad student was that when you have a systematic error, you really can't improve it unless you build another experiment, which is guaranteed to not do the main science goal that you have, which is to measure the inflationary gravitational waves, in my case, or other. So,
astronomy is hard in that way because you are an observer. You're not really an experimentalist. You go in a laboratory, you can change this, you can change that.
Yep. Controls and variables.
Control things. It's much harder to control the universe.
And especially when, the universe. When I was a kid and you were a kid, there was only one universe. Now we've got multiverses. Speaking of that, when I think about Fowler, I also think of his connection with my late great colleagues, the Burbages, who were at San Diego until 10 years ago in the case of Jeff, and 14 years when he passed away, and 4 years ago now Margaret passed away. And they worked very closely with Fred Hoyle, who of course coined the Big Bang and believed in panspermia and all these other things. But he's known for the Hoyle miracle, which is this process in the beryllium resonance astroparticle. A lot of people make claims that this is evidence for some sort of underlying architecture, some design in the universe. And I wonder if you're comfortable discussing it. Because Willie effectively found that, right? I mean, he experimentally led the campaign that discovered this beryllium resonance, which lasts for a femtosecond or so on. Is that really evidence, or does it fall to the realm of, out of the realm of belief and faith into the realm of evidence and science?
I don't think so. I don't think it's related to faith and, the intelligent design. The universe was designed to have this resonance in beryllium.
Maybe we should just say what that allows in the triple out. You want to take it away?
So this has to do with nuclear reactions. And Fred Hoyle realized in order for some specific nuclear reaction to occur, to understand stellar evolution, there had to be an excited state in beryllium with a certain energy. He sort of calculated what the energy would be, what the width would be, what the properties would be. And then an experimentalist, Willie Fowler, went off and found it. So, but it does seem, without that, stellar evolution would be different. The production of heavy elements would be different. The universe that we see would be different.
When we look at controversies in cosmology, there's a famous quote from Steven Weinberg, who you knew very well, and I want to talk about him and David Schramm also, of course, you knew extremely well. But Weinberg would say, physics thrives on crises, and unfortunately, there aren't many crises now. And I was just talking with Wendy about the Hubble tension and all these things. One of my favorite solutions to the Hubble tension, actually, in fact, my favorite solution, we're not supposed to have these. We're not supposed to have favorite kids either. My mom once said, I asked her, who's your favorite, me or my older brother? And she said, that's like asking me to choose my left hand or my right hand. I said, Mom, you're left-handed.
There was someone who had 7 children, and someone asked, who's your favorite child? And he thinks for a while and says, does it have to be one of mine?
Reminds me of a joke. A rabbi is on a plane and he's writing a book about how to raise children. And the guy sitting next to him, well, what do you know about children? What gives you this credibility to write a book on children? He goes, well, I've got 4 children. And the guy gets very sullen. He turns away and he goes, wow, I wish I had 4 children. And the rabbi's like, oh my God, did I say something wrong? Did you, God forbid, to lose it? He's like, no, I have 7 children. But one of the solutions to the Hubble tension comes from an area that you covered in the early universe, which was primordial magnetic fields. Mm-hmm. And that they can change and alter the sound horizon. They can do all sorts of things to the stress energy tensor. Talk about, how we are looking for these exotic things, evolution of dark energy or, some new physics and so forth. Is that like the last bastion of the scoundrel, or should we look for honest to goodness things we know about, like magnetic fields, to solve new tensions and controversies in cosmology?
Right. So we have a remarkably successful model of cosmology, the standard model of cosmology. I'm sure people on your podcast have talked about the standard model of cosmology. I hate it. Because it looks, once everything's understood, I'm out of a job.
Right, exactly, right.
What do I do if we understand everything? So there's a lot of effort in the community to try, we call it break the standard model, to see where the flaw is. So it's like the sweater, to find the thread that you're going to pull that unravels everything. One of them might be the Hubble tension that Wendy Friedman talked to you about. Then there's other little tensions that are coming up in the cosmic microwave background radiation. You could tell me about them, but you'd have to kill me, I guess, right? Yeah. Because the meeting's going on now. It's not public. But there's a lot more we don't know about cosmology. We don't know about inflation. Inflation's an idea we have. It's a great phenomenological success without theoretical underpinnings. We don't know the dynamics of the fundamental physics behind inflation, which is responsible for the fluctuations in the microwave background radiation that you study. It's responsible for the fluctuations in the matter density that grow to become galaxies, stars, planets, people, etc. You are in amplified quantum fluctuation.
That's right, the podcast.
But we don't really understand. We don't have any idea about the basic physics that drives inflation. Then there's dark matter, that most of the mass of the universe is dark. 25% of the mass and energy in the universe is dark. And we don't know the nature of dark matter. And it's a problem that's been around, an issue that's been around since the early 1930s. And in the past 20 or 30 years, it's attracted a lot of attention. I think for many decades, it was not considered a problem. Then people started realizing, hey, there's a real issue here. It's telling us something. What is the dark matter? And then there's dark energy that's driving the accelerated expansion of the universe. That's a real head scratcher. So is the standard model have these things that are not understood, but yet seems to describe the evolution of the universe? Or does it? Mm-hmm. So is there a Hubble tension? Is there another ingredient that has to be added? What about the role of magnetic fields that you mentioned? Mm-hmm. And turbulence and all these other things that you can put in to make a more complicated story.
And talk about another major theme in the book, phase transitions and so forth. What is a phase transition, and how did you come up with ideas in terms of relating them from something like ice or a hand warmer in the ski resort where I'm sure we frequent quite frequently? How could they possibly have relevance to the universe as a whole?
So we think that in the evolution of the universe underwent a series of phase transitions where the symmetries that started out in the early universe at high temperatures, there was more symmetry than we see now in the laws of nature. We call it symmetry breaking. But in phase transitions, one of the things that really excite me is the idea that there could be a remnant in the universe today of a previous phase. And this would be the inside of cosmic string, domain walls, magnetic monopoles, things like that, that have a remnant of what the universe was like well within the first second of the universe. And it's a beautiful idea, but we need observers to go out and find the darn cosmic string or something like that. So cosmic strings may be around. And in terms of going back to dark matter, people have ideas for dark matter that range over 80 orders of magnitude in its mass, something that's incredibly small.
Yeah.
Incredibly
Up
light.
to deep dish pizzas, dark deep dish pizzas.
Right. Good.
So, yeah, in that realm, one thing you've worked a lot on neutrinos, which are these ghostly particles that are irradiating us right now. But I always like to say, and maybe you'll slap me around, but I always like to say, at least we know there's one particle of dark matter, right?
Yes.
Neutrinos fit every single category that you need for dark matter. Doesn't that tell us that these alternatives like Mond and Tebes and all these, that they're sort of, a fool's errand?
I don't work on it.
Mm-hmm.
I don't think it's a productive way to go.
Mm-hmm.
I listen to it just to make sure nothing, being a little humility. I could be wrong about that. But I think modifying gravity is really hard. It's something I've thought about and worked on. Einstein's theory of gravity is a beautiful theory, and it's almost indestructible. Mm-hmm. It's hard to change it. So modifying gravity is a tough thing to do. Now, maybe the Einstein of the 21st century will figure out how to do it, but it ain't going to be me. I tried.
Yeah, that's right. Yeah, it's sort of, Einstein also tried to outdo himself, and that kind of brings me to my next question. A lot of times we hear about, in context of phase transitions, so forth, we hear a lot about the theory of everything. But as far as I know, we don't have even a plausible grand unified theory. So I always joke we're putting the toe ahead of the gut. We should really focus on our guts first. Can we solve and can we hope to unify laws of physics when we don't even? And obviously the heroic efforts of many people from this institution and around the world have contributed to the standard model, the core theory, as Frank Wilczek calls it, of particle physics. But are we really not kind of getting ahead of ourselves and really looking to kind of a level jump beyond our capabilities and looking for a theory of everything? Is there a theory of everything?
Well, that's a good question. Is there a theory of everything, or are there theories of everything? Now, my friends who are string theorists, or I don't have any friends who are string theorists, but if I did,
stay away.
They would tell me that there are many possible laws of nature.
Yes.
They call it the multiverse.
Yep.
And
Landscape.
we're just the landscape, right? We're just seeing one realization of possible laws of nature. Mm-hmm. So maybe there's not a single theory of everything, but theories of everything. Now, how do you prove that is the question that no one's figured out how to do. So maybe the next step is some unified theory. What's beyond the theories that we have now? It's called the electroweak theory, the standard model of particle physics. Yes. What's the next step beyond that? No one thinks that it's the final answer. Mm-hmm. So there are tantalizing hints, neutrino masses. Mm-hmm. We don't understand the origin of the asymmetry in the universe today between matter and antimatter. Mm-hmm. Maybe that's pointing the way to new physics. Inflation or dark matter. One of the reasons particle physicists are interested in dark matter so much is it could be the next step beyond the standard model of particle physics. Mm. Dark matter has no place to live in the standard model of particle physics.
That's right. It has to be an auxiliary, additional hypothesis. Was it possible for astroparticle physics to kind of come about before it actually did? In other words, it sort of came after, the high energy physicists kind of moved into cosmology and particle and astronomy. relatively late in the, go back to Brahe, in your book, right? I mean, it's 4 centuries, right? Was it possible? I mean, could they have in fact entered earlier? And I don't mean like the cosmic rays and stuff that were discovered in the 30s, but was it necessary for us to have a mature, quantum field theory, QED? Was that a necessary condition in order to have folks like you revolutionize by adding the tools and techniques of particle physicists to the world of astrophysics? Or, was it?
So I would go back to Willie Fowler and nuclear astrophysics. Mm-hmm. He introduced nuclear physics. Well, he and others, of course, introduced nuclear physics and championed nuclear physics in astrophysics. And nuclear physics can describe how stars work, Big Bang nucleosynthesis, where does the helium come from, where do the elements come from? And, we still don't completely understand nuclear physics, but we have a good understanding of it. But we had to have some understanding of nuclear physics before there was nuclear astrophysics. Mm-hmm. We had to have some understanding of particle physics before there was particle astrophysics or particle cosmology. And the understanding of particle physics, I think, really traces back to the Standard Model of particle physics, which emerged in the late 60s and early 70s. And shortly after that, people turned to cosmology and astrophysics because we had this tool that we didn't have before. Mm. So when I was in graduate school for the early universe, people talked about something that was known as the Hagedorn temperature.
Yes, the string theory.
Right, no matter how much energy there was in the early universe, the temperature was never larger than a certain amount. That's quite low by modern standards. And that if you put more and more energy into the universe, it would create, rather than more energetic particles, more massive particles. Mm-hmm. So there was a limiting temperature. It was called the Hagedorn temperature. And with the development of the Standard Model of particle physics, quantum chromodynamics, QCD, the theory of the strong interactions, people realized that there's not a limiting temperature and that quarks and gluons would get higher and higher energy earlier in the history of the universe. And that opened up a lot of possibilities.
Hey there, I know you're enjoying this deep dive into cosmology and scientific discovery and humility as well. And I have to maybe beg your indulgence and be a little bit humble myself to inquire why there are so many of you who have not yet subscribed to this podcast or YouTube channel. Found only about 50% of you are engaged by subscribing or following the podcast. And I'd really love to boost that number up closer to 100%. I am a perfectionist after all. I hope you'll consider subscribing wherever you're listening or watching this podcast. Now back to the episode.
Yeah, that's true. Yeah, now it has we've had Robert Brandenberger on many times, my former co-advisor from Brown, now at McGill. And yes, he's string gas cosmology and super string gas cosmology. I want to ask you sort of a philosophical question with a broad spectrum of history that you can draw access to, which is we are theoretically on the cusp of discovering the mass of elementary particles using cosmological observations. And to my knowledge, correct me if I'm wrong, there's 17 elementary particles. 14 of them have had their masses measured on Earth. None of them have had their masses measured off the Earth. Would you believe us if we came upstairs and I said, Rocky, don't tell anybody, don't tell the 400,000 people watching, we have measured the mass of neutrinos. Will a card-carrying particle physicist out in Batavia over there, wherever, will he or she believe what we have to say as cosmologists intruding on her turf?
They better damn well believe it. I would believe it. And I think the determination of the neutrino mass will come from CMB observations and astrophysics. It won't first come from particle physics. Mm-hmm. So, but there's sort of historical precedence for this in discovering elements. Mm. Helium, the second most abundant element in our universe, was discovered. Helios, by looking at the sun.
I thought they went there at night. Can you go there at night? Because I tell my kids at least. Right. So yes, that's true, and of course muons and cosmic rays,
and cosmic rays, and things like that. Mm-hmm. So they should pay attention, and I think it's going to be a very exciting time when we know the mass of the neutrino.
Yeah, absolutely. I mean, it's 3/17 of the. Will it mark, as Kuhn would call, a paradigm shift? I mean, would it be? Is it like? I mean, imagine if a botanist came to you and said, "I know the mass of the neutrino." I mean, you might respect their botany, but I don't know. I'm just making this up. But astronomy is radically different. I mean, we're looking at correlation functions of little smudges on the last scattering surface, and it's not, so obvious. I think you're right that, we better make them, we better do a good enough job that they have no reason to doubt us. But.
So your measurements are hard, and you say you're looking at little smudges and this and that, but look at the collisions at the Large Hadron Collider, producing hundreds of particles, and they have to sort through this and this and this and this. So it's hard. The bleeding edge of science is also the leading edge of ignorance. You really have to struggle.
You mentioned something in passing in the string theory landscape and the multiverse. So in one case, the multiverse is a consequence that seems to be built in part and parcel. You've got to accept it if you accept inflation. I've had Andre Linde on the podcast, and I've talked to Alan Guth privately, but he hasn't yet come on. Hopefully he will soon. But they both kind of admit you get it concomitantly with inflation. How do you feel about that? There are those that, like your probably Caltech contemporary, Paul Steinhardt, a very good friend of mine, who don't believe that the multiverse is not only a good thing for physics, but he thinks it's bad for society, the scientific method. I'm not asking you to comment on Paul specifically, but is the multiverse something that gives you pause, or is it something that's exciting?
Well, it's certainly a head scratcher. I think the idea of a multiverse is almost unavoidable if you in inflation. So if inflation, as most people envision it now, had anything to do with the early universe, a multiverse is almost inescapable. Now, there's another question. If you create other universes, will the laws of nature, the laws of physics, be different in those other universes? And people usually conflate those two. But you can have a multiverse without having laws of physics different in different universes.
I asked Andre, kind of just to, I don't know, kind of take my shot at the king, and I said, why stop at physics? He always says, why should there be a universe? It should be a multiverse, and you have to convince me it's a universe. It should be a multiverse. And so I said, well, why stop at the laws of physics? Why shouldn't modus tollens vary from universe to? And he was like, I don't think math would vary, but who knows if it's true that we actually know as much as we know about math from the physical universe, and that dovetails with the famous quote by Eugene Wigner, commented on the unreasonable effectiveness of mathematics in the physical sciences. We take it for granted that, of course, you're going to use math. You got to be good at the calculator and the pencil, right?
It's a great tool.
Yeah.
Will it be the tool of the next century? So I have a friend, Stephen Wolfram. I don't know whether
been on the podcast many times. Yep.
Okay.
Another Caltech.
Right. Well, we collaborated together at Caltech. I've known him for a long time. And he thinks computation is the way to go.
Yes.
And I've always told him that suppose in 1667, sitting under the apple tree in
Woolsthorpe,
England, with Newton's mother's home,
right.
If instead of an apple falling on his head, an Apple computer had fallen on his head, how would science have been different?
Right. And I asked that question of many of my colleagues that work on artificial intelligence, because, if you ask, if you recall, or I'm sure you do, Einstein said the thought that titillated him the most, the one that gave him an exhilaration up his spine, was that an observer in free fall would experience no gravitational field.
The greatest thought of his life. The happiest thought of his life.
So I asked my colleagues that are artificial intelligence, optimists that believe that we're on the verge of AGI and Turing test is going to be obliterated and so forth. I asked them, well, in what sense could this computer, if I pick this computer up and put it in free fall, I can predict exactly what's going to happen to it. It's not going to be happy, but to what extent?
Free fall is fun.
Yeah.
It's the landing that is not going to be happy.
It's at the end is a doozy, as they say in Groundhog Day. But the question I always have is, how could a computer understand the concept of happiness. What do you like? Rub its capacitor in a certain way, or and second of
I
all,
thought this was a PG.
that's right. Yes, I've already violated that norm. So how could it experience and the embodiment? Which with some like Noam Chomsky, who's been on the show as well, has said is essential for not only for communication and computation, but for consciousness. So I ask this question maybe in the context, you're not an AI expert, but in terms of tools that we'll use in the future, as our profession is 1,000 years old. I mean, you and I are doing, I call it the second oldest profession, right? After, what? No, I'm going to keep it PG-13. But, back in Bologna in 1080, they were scratching on blackboards and with rocks. Right. We're not doing that much different. So how do you see our profession as faculty, professors, and whatnot? A lot of my audience are faculty or aspire to be. How do you see it changing? What can artificial intelligence add? Can it do what you do as a theoretical physicist?
I think eventually it will do much of what I do. Hopefully not soon, and hopefully I can retire and not be pushed out for because somebody has a better computer. Yeah, I think it's going to be a real tool in the future, not just for data analysis and things like that. It already is a big tool, right? Yeah. But in coming up with new ideas and theories, it's going to see things, I think, that we don't see in our usual way of thinking.
When we think about, kind of the biggest mysteries, I like to give you the option. You talk to the old one, as Einstein would call God. And, you could get one answer out of God. What's the most mysterious thing that you've encountered in your career? The thing that you're most keen to get the answer to before you get emeritus status? Say?
Well, I have a bunch of questions. Like maybe
you only get one.
Maybe why is there a universe?
Interesting.
I'm sure happy there is a universe.
Right.
At least one. I'm happy with just one.
That's right.
But why? Why is there a universe?
Yeah, it could have been otherwise.
Yeah.
Again, these always dovetail into questions of purpose and teleology and meaning and if there's existence. And those are the things we never give our students the chance to actually ask or answer us because they're too busy solving integrals in grad student revision.
Physicists are good at answering the question of how.
Yes.
Why is a more difficult question to answer and something that's not really part of what we do.
Mm-hmm. Do you think, I look at my colleagues and we don't have a law school, thank God, at UC San Diego, but we have a medical school.
You're lawless.
That's right. It's like Mad Max down there, Rocky. I don't even know how to describe it, but we have, my brother's a lawyer, right? So, but they teach ethics. They teach, kind of like, how do you be a scientist? What's the practice of that craft, of a lawyer, of a doctor, even of a businessman or woman, right? The ethics are taught. We never teach that. We never teach about research ethics. Rocky, my advisor's got to get tenure, or I got to get my job for my student because otherwise it'll look bad in my. How do you handle that? Or do you ever encounter those situations where we are not really trained to deal with these things, and yet they're very common, right?
It's very important too. And I think the way most people experience and learn it is through osmosis. Mm. And I think it's the responsibility of those of us who are in responsible positions to demonstrate ethics and responsibility and maybe kindness and humility, and maybe our students and postdocs will pick that up. Mm. I don't think it would be good. Okay, so today we're having a lecture on ethics, and work these two homework problems, and you'll have one problem on the final exam on ethics. I don't think that's the way to instill ethics in people.
Yeah, I even talked. The worst class I had, the only class I didn't get high marks on in first quarter freshman year at Case Western was philosophy, and this professor was like, he looked like Gabe Cotter from Welcome Back Kotter with the hair and the mustache and everything. No offense, but he would only give true and false exams in philosophy. So it'd be like, the categorical imperative is necessary for you to have this contingency. Like, true. And I would get less than 50%. Every single exam I got 25.
How could you get less than 50%?
It was so over the top. Yes, so it's probably good that we don't delve into those waters. When we look at kind of these mysterious things, a lot of times people will say, you cosmologists, Rocky, Brian, you guys are so, cocky about what you do, but there's 95+% of the universe you know nothing about, even by your own admission. I mean, dark matter, we can say a neutrino, but really you know nothing about it. And then dark energy, the square root of nothing, or maybe even less. So the logarithm. So tell me, how would you answer those kind of critics? Standing on one foot, what's the answer to such accusations?
Well, from my personal life, finding the answer is great, but the voids to find the answer I find very rewarding. And I think we should have humility about what we don't know. And I like to give public lectures about what we don't know. And I think it's a mistake to go up in front of a general public or a class or something, or even graduate students in your field, and say, oh, we know all this is what we know this, but there's the vast ocean in front of us that we don't know. And I view, so I give a lot of public lectures, and most of the audience are not scientists, and they think I know so much more than they do. But I think, it's just it's like the last several inches of a mountain that I know, but they know a lot also.
Yeah.
So, I always try to respect the intelligence and curiosity of my students in the audience. I think that's important for us to do. And if you come across as being arrogant, it's a terrible thing.
It is, because the one thing that a layperson can have is curiosity, just like a scientist. And you're renowned for your public lectures and also your technical lectures. As we come to the final 3 or 4 questions, one thing in the zeitgeist nowadays, I don't know if you've encountered this, is the concept that the Big Bang never happened, that we're all just shills for big NASA. I wish we could get some kickbacks from.
We're not getting enough money if we're shills. I mean, where's the money in this?
Well, we're hearing this Pritzker, appointed. I wouldn't speak too loudly from UC perspective, at least U Chicago, not UC California. But have you heard this? That they claim that either the universe is twice as old. I've had on Rajendra Gupta from University of Ottawa, who claims that no, actually we need tired light plus plus dark energy. Have you encountered this concept that the Big Bang, we can explain things via tired light, and that actually it's a better fit in some sense to observations? Yeah.
So I say I don't think the Big Bang is the complete model. Well, we don't know everything, and but I think it's going to be part of the complete model. Just like Newtonian physics is not a complete description of the world, but it's part of a complete description of the world. We still teach it, right?
Yeah, it gets us to the moon, right?
Yeah, right. It got us to the moon. There's got to be something right about it.
Right.
So I try not to, but people seem to be, there's a feeling, a zeitgeist of people against experience or experts.
Yes.
Authorities.
Authority,
like that.
100%.
And I think it's not just in our field, but in every field.
Public health.
Whether it's epidemiologists or what have you.
Global warming, right.
What do those idiots know?
Right. Yeah. It's where when a scientist become political scientist, that's usually a challenge as well. So you recently celebrated the 10th anniversary of the KICP? Is that
the 20th?
20th. Sorry, 20th. Yeah. So talk about that. What is on the menu? You've been a director of it, as you've done many things. What's the future hold for this great institution?
Well, that's the right question. So we celebrated the past, but we also want to know what's going to be the future. Yeah. I think here at Kavli Institute and University of Chicago, I think that we have been the center of, maybe one of the centers of cosmology, and the students we've trained, the people who have come through here, and the science that's been done here. And what is going to be the future? And I think it's going to be different. As a cosmologist, I try to predict the past. Predicting the future is even more challenging than predicting the past. But it's incredible to me. So when I started out in cosmology, there were many more theories and ideas than there were experimental data or observational data to test them. Now there's data all over the place, coming in all the time. Thank you very much.
Yeah, flood of it. Yeah.
We're flooded with data. And it's a different world now. So, when I first started doing particle cosmology, I could write a paper every night because there was no data to disprove it.
Yeah.
Now it's so hard.
Yeah, but it's exciting too.
So the future is going to be more and more data, larger and larger collaborations, and more and more expense.
Yeah.
So
Going to look a lot more like particle physics in some ways.
Yes.
Big collaboration. So as we wrap up, I like to ask two questions to all my guests that grace me with their presence on the Into the Impossible podcast, and they connect to different sayings of the great Sir Arthur C. Clarke, who is the namesake of this podcast. So the podcast is called Into the Impossible, and that's from one of his aphorisms that said, "The only way to determine the limits of the possible is to go beyond them into the impossible." But he said other things too, like any sufficiently advanced technology is indistinguishable from magic. And I want to kind of use that to ask you a question, a version of Feynman, your former teacher and friend, I'm sure, at Caltech. He used to say, what sentence contains the most information in the fewest words? And he would say the atomic hypothesis and everything. But I want to ask you, if you had to make a billboard, about the greatest technology, science, discovery, ethic, whatever you want, say that happened on Earth, what kind of swagger, what kind of bravado would we have the chutzpah to declare is the most magical thing that you've encountered? Maybe your career or maybe someone else's.
Well, I think in general is the development of quantum mechanics. So I think general relativity was a tremendous intellectual accomplishment, but in hindsight, it would have been done. If Einstein hadn't done it, I think other people would have.
Others were on the trail.
Quantum mechanics, we still don't understand it.
Right.
Where did this idea of the uncertainty principle and the correspondence principle and just the simple things like the double slit, is it a particle or is it a wave?
Right.
I think the development of quantum mechanics took a lot of people. There are some people made larger contributions than others. You can list Bohr, Heisenberg, Schrodinger, Lisa Meitner, people like that. But the development of quantum mechanics was amazing to me.
Yeah.
I think that's the most remarkable thing. It makes me proud of our species.
Yeah, that's
and
right.
There's not many things that makes me proud of our species.
Nowadays, yeah. Well, it does remind me the day after Einstein died, Time magazine ran a cover and there was a picture of planet Earth with a giant sign that said Einstein lived here. But of course he was wrong about most of his things in quantum mechanics. Right. And that's a cautionary tale that, I'd like to make blunders on the level of Einstein's blunders that turn out to be, Nobel worthy.
He was wrong, but he wasn't stupid.
Yeah, he was. He was an incredible intellect. I mean, he's very much, lionized in the public, but he's also amongst physicists. I mean, they just cannot escape the admiration that we have for him. And it's quite well deserved. So the last quote is not the one that I will often levy on my department chair from Arthur C. Clarke, which is when he said that for every expert, there's an equal and opposite expert. So I like to drop that from time to time. But no, he said the following. And he said, and I'm not calling you old, God forbid, Rocky, but he said, when an elderly but distinguished scientist, I'll call you distinguished, scientist says something is possible, he or she is very much likely to be right. But when he or she says something's impossible, very much likely to be wrong. So I want to use that as an opportunity to ask you, what have you been wrong about? What have you changed your mind about, if anything?
I'll go back to when I was in graduate school. As a postdoc at Caltech. My biggest disappointment was the experiments that were looking for proton decay. This was in 1982 or something like that. Didn't find it. I was absolutely convinced they would find proton decay. It was such a beautiful theory. It was a grand unified theory. It was a way to understand the asymmetry between matter and antimatter, the baryon asymmetry. I thought, sure, they would find it, but they didn't. So I don't know what was wrong with those experimentalists, but they didn't find something that was theoretically beautiful. You can have, nature's like that. You can have a beautiful, elegant theory, that turns out to be wrong.
Yeah, didn't Eddington once say, never believe an experiment unless it's been confirmed by theory?
Right.
Turning the aphorism on its head. Well, Rocky, this has been a great joy, as I knew it would
fun.
be. And I hope to maybe see you again in San Diego or back here again.
Okay.
I'll do a part 2. This has been a great joy. So thank you so much for joining.
Thank you.
If you watched all the way to the end, I know you're going to love my interview with Rocky's colleague, Adam Reese. And click here for a playlist from the best episodes in the past few weeks. Go on, click it.